All right. All right, so let us start for today. So first of all, before we start, I would like to introduce you to the book of the day. So this book is called Intermolecular and Surface Forces, and it has been written by Jacob Israelashvili, who unfortunately passed away very recently. So it's a great book about surface forces and interactions. Really, when you deal with soft matter and confined system, you have plenty of effects such as van der Waals forces between two substrates. You have ionic forces between the charges of your surfaces and the charges inside the solution, and we will discuss that later on. But you have plenty of forces that appear at small scales, including Casimir forces, for instance, and that are really completely detailed in this book. So I would really recommend you to have a look at that, especially if you work in surface science. That's for the book of the day. For the tutorial of today, what we would like to study is the effect of confinement. We want to study a chain, a polymer chain, a macromolecule, an object that has been already described by us in the previous tutorials. Yes? Any question? Can you unmute yourself? No? Just showing me the video? Good. Hello. So now we would like to study the problem of a chain confined in a box. And in this nice paper by Sam Edwards, who was a famous physicist at the time of De Gennes, actually, they were working on similar topics, wrote these very elegant articles where he starts to calculate the statistical physics of polymer chains. And he introduces an analogy between the polymer problem and the Schrödinger equation. So this is another toolbox that I would like to introduce to you today. As you can start to feel, I'm always taking the example of polymers, but this is a way to introduce new methods that might be useful to you. And this one is really introduced at the end of his paper. So if you have a look, you will see in the appendix of that paper, here is really describing the problem as a Schrödinger-like equation. You can see here the operator is a Schrödinger-like operator, and you have all the basis of solution. So have a look, and we will put this into practice today in the tutorial number 5 that you should have in the Dropbox. So please take it. There will be a small reminder about quantum mechanics, but it will go pretty fast, and then we will be back to polymers. Okay. So here it is, and let us start with the whiteboard now. All right. All right. Okay, so the problem we want to study is the following. We consider a box in space. This box is a box in 3 dimensions. So it has a certain volume that is really the product of the 3 length scales or the 3 sizes of that box in the 3 directions, okay? In this box, we place some polymer chain. And at the end, we would like to look at the problem where the box size becomes comparable or even smaller than the typical polymer extent. So the radius of gyration or the end-to-end radius that we discussed so far. Okay, so this is a situation of interest because you can think about biology where you have DNA, for instance, inside viruses, where DNA is completely coiled and confined into a capsid, or let's say a little box. And the statistics of those chains are pretty different than from the bulk, because due to the wall, or the walls all around, you have a restriction of the number of conformations, you have a folding of the chains, and so on and so forth. Similarly, you can also think about very tiny nanoplastics. You can fabricate samples that are films that have typically a nanometric length scale, and those polymer chains, they have 50 nanometers in typical radius or more. So you start to confine really your polymer chain into very small samples, and there again, the rheology, the stability, for instance, if you want to store information inside this by putting some little holes, by imprinting some information at the nanoscale, for instance, because you want to have a new storage device, well, you want to make sure that the information doesn't pass away. So you want to make sure that the viscosity is pretty high or that the rigidity of the sample is pretty important. And therefore, you need to understand what is the behavior of individual polymer chains and then entangled polymer chains and what is the typical timescale for relaxation and so on and so forth. So the topology will matter a lot. Okay, so this is a problem of importance, as you can see, in biophysics and nanoscale physics or nanotechnology. All right, so let us just specify a few aspects. Here there is a starting point, which is R prime, and there is an ending point, which is R. So so far we were fixing the origin of the polymer chain and look at the extension. Here now we will assume that this can just jiggle all around everywhere, and so those two extremities, they are free. The second aspect that we would like to deal with is that we are interested, as usual, in the probability of starting at R prime, ending at R in n steps, with n being a very large number. So this is the same problem, apart from the fact that we have really a wall around for which there is a zero probability strictly to be outside or to touch the wall if you want, okay? All right, so let us start now if there are no questions on that. Yes, it's clear? All right. And so let me remind you the bulk reference case. So in the bulk case, which is tutorial number 1, and let me also specify that we are dealing here with an approximation. We are dealing with the ideal chain. We don't consider the fact that there are interactions with solvent and so on. Here we are looking at confinement effect, so we don't want to put too much complexity. Let's first understand what is the confinement effect on the ideal chain, and then if you want, you can mix all the ingredients we've discussed so far. Okay. So the bulk result was the following. First of all, that probability was satisfying a diffusion equation. Okay, so we had the Laplacian of the probability with a sum diffusion coefficient, which was related to the size A of one monomer to the squared, was equal to the derivative with respect to the total number of monomers. So it was a diffusion equation for which the solution was obtained, and in 3D, this had the following form. There was a norm. Please check the prefactors. Yes, it was n a squared is the variance, and then you have the Gaussian behavior. So r minus r prime to the square. There was again this variance that should appear without a pi here, and I guess that was it. What we were discussing so far was the end-to-end radius, and so we were calling that object capital R, but this is exactly the same. Okay. So this was the probability for finding a certain extent, and it was only depending on the difference between R and R prime. Okay, so it's a problem that was invariant by translational symmetry in space. Okay, so the initial condition was the following. Initial in the sense of having 0 monomer, so time here is the number of monomer, and this was to obtain the solution above, we had to satisfy this initial condition. Okay, so basically the probability of going from R prime to R in 0 step, well, is a Dirac centered on the starting point. Okay, and then we have also the spatial integral. So yes, so we would like to study just this guy. So now we have to remember that P was normalized only with the final point because we were fixing the origin to 0. Now there is another extremity that is free to move. So the first integral will give 1, but the second one, sorry, here there is a typo. The second integral provides the volume. So in a sense, you were saying that, and this volume was infinite, but the integral of the probability, which is, if you want, the partition function of that problem, is simply the total volume, which is interesting because it says that it's pretty much like an ideal gas. So that is why the connection with the Schrödinger equation will come in a minute. All right. This, I can call it partition function if you wish. So now what happens if you are in a box? Which of those results will be modified? Now we are in a box like that. So according to you, should we conserve the governing equation here?
Yes.
Yes, there is no reason for not changing the bulk equation. So what would change? Of course, this won't be true anymore, right? The solution will be modified by the presence of boundaries. The starting point will be conserved, and this we discuss after. So what should we add with respect to the bulk situation? To express the fact that you have impermeable walls.
Boundary conditions on the value and the derivative of P.
Yeah, so we could choose between the value like Dirichlet or the Neumann ones. We will take the values. So we will assume that if the polymer touches the wall, okay, really like the molecules are inside the wall, then the probability is 0, okay? So we will say that the probability of, let's say starting here, this is R star, and let's say this is the final point R. R star, R in n steps is 0, and this is true for any n, any R star belonging to the wall. So the volume being, let's say, omega, I can call that, or V, I can call that delta V. So delta V for me is the surface of my volume, and any R belonging to V, okay? So this is true. This is also true for the ending point, and there is a perfect symmetry here. So I can start at any R prime and end up on the wall in any number of steps, and this should be 0 as well. So it's also true for any R prime belonging to the volume. Okay, so that's the main difference. So now we have really a box that says the chain must be inside the box. This is trivial, but it will modify completely this result. The probability won't be anymore equal to the Gaussian. Okay. Okay, and now comes the intuition by Edward. Look at that. This looks like a trajectory of a particle inside a box, first. Secondly, if you look at the equation, this resembles a Schrödinger equation. You have a single derivative, let's say in time, and apart from prefactor, you have a Laplacian operator, which is, if you want, the kinetic energy in quantum physics, and there is no potential because you are free to move everywhere inside the box without feeling any potential. The potential is uniform inside the box, it is equal to 0. So there is a strong analogy with the Schrödinger equation. Yeah. And the problem of a single particle inside a box, which is a problem that you all have studied in your quantum mechanics part 1. Okay, so let us describe more precisely the relation. So first of all, Schrödinger's equation is the following one. If I derive the state function of position and time with respect to time, this is proportional to the kinetic energy, and this is the Laplacian of psi. Okay, so this is Schrödinger equation for a state or wave function phi. All right, so this is a bit different from what we have here. Here, as you can see, we are dealing with an object that starts at R prime and ends up at R. So what we would like to study is rather the probability to be at R prime at a certain time t equals 0, and then end up at R at a certain time t. Okay, so this would be the analog. So let me introduce that guy. It's called the propagator because you propagate from one point to the other. And so you start at R prime at 0 and you end up at R at t, so it depends on those three quantities. This can be formally written as, I want to be at the same time starting at R prime at t equals 0, and then I would like to be at R at t. So those are the two constraints, and I just factorize the two. Okay, so this is really now the probability of starting at R prime at t equals 0 and ending up at R at time t. And interestingly, all the variables here are time in the partial differential derivative here, and here it's a Laplacian on the coordinate r. So there is no r prime, so this will be a factor that is constant for the Schrödinger equation. So we can really apply the Schrödinger's equation to G, okay? And you end up with the fact that you have the Schrödinger's equation exactly like the previous one for G as well, okay? And G is called the propagator. All right, so now we have this equation, and I'm interested in the polymer problem that says that, well, I have this operator. Sorry, typo here, up. G being a function of r prime, r, and time, while P is a function of r prime, r, and n. All right, so everything is clear now. We have a lexicon to translate from the quantum problem to the polymer problem. We can say, for instance, we can divide by h bar everywhere, say that IT is mapped into number. Here, G is mapped into P. What else do we have? We have h bar over 2m, which is mapped into the diffusion coefficient of the polymer problem. All right, and with that dictionary, you have really a correspondency between the two problems. They are strictly identical, provided that you transform time into a complex time. But this is just a mathematical trick. So this implies that if you are able to solve that problem with the proper boundary conditions, meaning for a quantum problem, having the wave function that vanishes on the wall, this is really the problem of a particle in a box where you have infinite potential on the walls, if you want. Well, if you're able to solve that, then you can just put back the dictionary and come back to the polymer world, and you have the solution. And since we all studied the quantum particle in a box, the solution is straightforward, okay? So we will have to just recall all the details, but this is the lexicon. Any question on that? Is there something unclear here? No? So let us go on. And
sorry.
let us, oh, yes, please.
Yes, sorry. Can you repeat the boundary conditions? Can you re-explain that?
Yes, so that part, right? Here.
Yes.
So first of all, we were, forget about the drawing here, just look at that. We were, in the tutorial number 1, we were in infinite space, okay? We were solving the diffusion equation in infinite space, and we obtained a Gaussian, okay? That's the basics. Now we would like to see how this Gaussian behavior is modified if now I'm not in infinite space anymore, but in a little box. So here is my box, and the polymer chain is inside. I'm just saying physically that this box, assume it's really a box with hard walls, the polymer should be inside. You cannot have conformations like that. Otherwise, this is not a box anymore, it's a porous box, okay? So to satisfy this description, I'm saying that each time a polymer will touch the wall, this is a configuration that has 0 probability. That is what is expressed here.
Okay.
Okay? So it's strictly saying that it's impermeable. You cannot have you don't find a chain that touches the wall or that is even behind the wall.
Okay, thanks.
And for the quantum problem, it's clear it will be the same. We will say that the particle is inside the box and that the potential on the box is infinite. It's really an infinite trap. So the wave function should be 0 strictly at the border. Okay. All right, so we have the lexicon and we can now start exploring this analogy. So we will just go inside the quantum world for a few questions. Let's say 2 or 3 or 4. All right, so as you know, when we want to deal with that operator here, the Schrödinger's operator, we want to find a good basis of solutions. So we introduced eigenmodes that have a constant energy. We call that eigenstates, and the energies are the eigenvalues. So what we will do typically is that we will introduce some basis solutions that are the following. You have an amplitude that only depends on space, and you have a phase that is provided by the energy. All right. So this is the typical state, and this again, psi nu is a function of both r and t. Okay, so now the propagator I was introducing to you before in that state, really I'm specifying now one possible solution of the basis, is the following. I have, remember, phi nu star expressed at r prime and 0, and psi nu at r and t. So this is, you have just the product of the two amplitudes with a conjugate, as clear from the quantum world, and then you have this phase with time. Okay, and this phi, sorry, is corresponding to that state. I'm only considering the new state. Okay. So now we would like to see if phi nu, now the amplitude, the spatial part, satisfies some equation. So let us just rewrite the Schrödinger's equation. This is written this way, and this is simply phi nu multiplied by the derivative with respect to time. There is minus I that kills this I, there is h bar over h bar, and you have E nu that appears in front. Okay? And on the other side, what do you have? You have the Laplacian of psi nu, well, which is only applying, and sorry, there is this exponential that is here. And you have the same here, you have the exponential that doesn't matter now. And you end up with the Laplacian of the amplitude. Okay, so basically the solution should satisfy the spatial and here I should have a minus h bar squared over 2m due to this guy. All right. So this could be rewritten the following way. You have okay, it's an ordinary differential equation of order 2 on the spatial amplitude. All right, this should be familiar to everyone here. Then, so the next question is to decompose that into the three directions of space, x, y, and z. So we have a problem that is really independent in the three directions. There is no potential here. The kinetic energy is really separable. So you end up with the following suggestion that, in fact, I can decompose that into a x problem with a certain index or quantum number that we'll discuss in a minute. Another one. And for the z direction, another one with another index that we will discuss in a minute, q. So we really decompose the problem into the three directions, and we assume that they factorize out. And for the energy, it's the same. It will be the sum of the energies of each of the one-dimensional problem. So this is thanks to the separability of the problem here. All right, and so we can rewrite the equation above. So you see that if I plug this expression here, I end up with, let me put out the non-dependent terms on x. So you have the second derivative with respect to x of phi Lx. Plus in the Laplacian, you have another second derivative. So let me now put Lx qz and the second derivative with respect to y now, and then it applies on py. And then you have the third part of the Laplacian, so on z. So all the other dependencies just go outside. It's a p here, y. Second derivative with respect to z of iq of z. So this is the Laplacian, and this is equal to, adds EP over h bar squared plus EQ over h bar squared multiplied by total phi. So phi Lx, phi Py, and phi Qz. This is equal to 0. All right. And now I can really divide everything by that quantity. If I do so, this will cancel, this will cancel, and I will have phi L here. This will cancel, and I will have phi P here at the denominator, and here this cancels, and I have phi Q. So in fact, you end up with a sum of 3 equations. That is the separability aspect. And let me write, for instance, this one. You have, so those are not anymore partial differential operators. They are total derivatives. So I can write them this way. And same for the couples, let's say Py and Qz. You can rewrite exactly the same equation for those other directions of space. All right. So we end up by solving a purely spatial problem, so with ordinary differential equations. And this spatial problem is the following one. It's a 1D particle that lives inside a box, and you have here only the kinetic energy. There is no other potential. And you have that plus boundary conditions. The boundary conditions are, you want phi L, let's say, for x equals 0, and phi L for x equal the size in the x direction. Okay, remember the volume is Lx, Ly, Lz. It's the product of 3 length scales. We want that to be 0. The function vanishes at the boundaries of the box. Okay. So now we would like to solve that equation here with the boundary condition. So I can introduce here a wave vector. So I can say that 2m EL over h bar squared is equal to KL squared, which is equivalent to saying that the energy in mode L is h bar squared KL squared over 2m. Well, it's the kinetic energy. You recognize the momentum and 2 times the mass here. So it's pure kinetic energy. And the solution of that equation, well, it's a linear equation with 2 derivatives here. So you recognize the sine and cosine. So it seems that it has to be something like A sine KLX plus B cos KLX. All right? Very classical problem. You remember the guitar strings inside your quantum well. Now the boundary conditions, FL of 0 equals 0 implies that, well, this doesn't contribute, but here you have B equals 0. So you can really forget that term. And the second one, you have quantization, sorry, which is related to that boundary condition. So now A sine KL times Lx should be equal to 0. So this implies that KLx is equal to L. Now you understand why it was noted L. This is an integer, should be equals to L pi over, sorry, it's Lx here, not X, with L being an integer. So also it should be a positive integer. Otherwise, if you have 0 here, it means the wave vector is 0. So sine of 0 will be 0. And so your wave function is badly defined. Its integral will never be equal to, I mean, the integral of the squared of the wave function will never be equal to 1. Okay, so we should avoid that trivial situation. And this is equivalent to saying that the wave vector is L pi over Lx. Okay, so this is quantized. And it says here that the energy is h bar squared over 2m times pi squared L squared divided by Lx squared. Okay? So we have identified the energies of the problem and the solution here, the wave function. We can normalize it though. So let us finish. Phi Lx is equal to A times the sine of pi over Lx times L times X. And this should be normalized properly. So if I integrate over the 1D box, this should be equal to 1. Right? And without any loss of generality, I can assume that A is a real number because the constant phase would not matter here at this stage. So I assume it's real, and I mean, I have the same basis with the same degrees of description. All right, so this is A times 0 Lx of sine squared of this quantity. That should be equal to 1. And this is equal to A times, so sine squared, I can decompose it into two terms. It's 1 minus cos 2 times the argument divided by 2. And here we are integrating over Lx. So this is one period of that cosine. So the average of the cosine is 0 here. The integral is 0 because I average over one period. So I'm left with 1 only. And so this says that A over 2 times Lx is equal to 1, which says that this is a A squared, sorry, due to the phi squared here. So this is a typo. This says that I found the amplitude, the prefactor of the wave function, Lx sine all right. And this is basically it for the quantum aspect of the problem, okay? So I'm sure you know that. It's just a reminder. If not, please just go back to your preferred quantum mechanics introduction book, and you will find this result. This is one of the few calculations we can make analytically. All right. So just now we have basis. It's not anymore a quantum problem a priori. Let us just check that if I multiply two different wave functions, let's say I can take n here. This is the scalar product. Okay, so let me check what this provides. So I have 2 times the prefactor here, which is a real number. So I have 2 over Lx. And then I integrate the sine L pi x over Lx and the sine same, but with an n over dx. And I can do a change of variables very quickly. So you see that you have each time pi over Lx. So I can really multiply it by pi over Lx here. And so Lx over pi. And call that object u. So I'm left with this integral. This cancels out. So I have 2 over pi. Integral between 0 and, if u goes from 0 to Lx, this x goes from 0 to Lx, it means that u goes from 0 to pi. Du sine Lu sine Nu. All right, and in fact, this is a known product. You can have a look at the formulas at the end of the tutorial. So they are provided on the last page. In that case, this says this quantity, I mean all the quantity, is equal to Ln. So we really end up with the fact that we have an orthonormalized basis of solution. So it's all safe. It's just a check, sanity check. All right. No question on those reminders? Feel free to interrupt. Huh? Okay, let us continue then. So now we end up with calculating the propagator. So what I would like to do, I introduced to you before the total propagator, which was the probability from starting at R prime and ending up at R at time t. And we said it was basically the product of phi star R prime at time equals 0 and ending up at R and t. This is general propagator. Now I've specified the state nu, so it's one solution, one canonical solution. So I would like to introduce G nu, which is the propagator for that particular wave vector. So it's simply in the new state. Right, and the new state is both an amplitude and a phase. So the spatial amplitude is phi nu written at R prime. Then you have phi nu at R, and then the phase with the proper energy. And this can even be decomposed further because we know everything. Now, this is in fact phi L of X prime star. Then there is the Y part with another index. And then there is the Z part, Z prime part, sorry, with another quantum number. Now for the other spatial amplitude, you have phi L of X, phi P of Y, and phi Q of Z. And then you have exponential minus I T over H bar. And you have the three energies, so EL plus EP plus EQ. So as you can see, it can be factorized. In fact, you see that it's really, the three directions are factorized. We knew that from separability. You have the X factor, which is basically that part. And then you have the Y and the Z. So we can really recast that into a product of GL of X prime, GP of, sorry, this is badly written, and T, GP, and GQ for the Z part. Okay, as you understood. So what I put in red here is in fact GL. and I can even specify it because I know all the phi L and phi L star of X prime. They are those functions. So since I have two of those, I will have this to the square, 2 over Lx. Then I have the signs. So pi L, because I'm in state L, X prime over Lx. Then the other one, which is this one. And everything is real here, so the conjugate value doesn't have any meaning for us. And then there is the exponential minus IT over h bar of EL. And EL, remember, is h bar squared, pi squared, L squared over 2m Lx squared. So I can simplify this guy out. Okay. Any question on that? Any typo? Perhaps I made some typo. No? And you have the same for y and q, and I won't do the 3D each time. I mean, it's factorized for the 3 directions of space, so I will only focus on x each time. It's simpler, and it's the expression would be very long otherwise. They are strictly the same. Okay? So the propagator, meaning this function, in the new state is decomposed into propagators for each directions. So L state for X, P state for Y, and Q state for Z. Remember that the new state in 3D is in fact a triplet. It's 3 quantum numbers, P and Q, 1 for each direction, and it provides you one list that corresponds to one 3D state, okay, new. And so we know the propagator in 1D that is written here for state L. That's for one particular state of the basis of solution. All right, we would like to transform that into polymer and forget about quantum now. So remember the translation, it's written here. So we want to transform the complex time into real time, G into the probability that I'm interested in, and the diffusion coefficient into the proper polymer one, okay? So we want to transform that in this solution. So P of starting at R prime, ending at R at time, after n monomers, well, is exactly like before. It will be the product. So in state nu, it will be the product of a problem along X, problem along Y, and problem along Z. So you have, let me call it PL, small p, and this is capital P. PL X prime X N, P Y prime Y N, and PQ for Z. And so it's equivalent if I provide you only that, because everything is identical afterwards. So this is the transformation of that guy, but in the polymer language. So 2 over Lx doesn't change. The box has a size in both problems, quantum and polymeric. Same here, those quantities, they are the same. They are the same. Only here you have IT that will become N, and the mass and h bar should disappear. You will have the diffusion constant here, okay? So let me rewrite it this way. You have 2 over Lx. The signs are identical. The 2 of them. And then I have this exponential, which is now, so this is time, it's minus n. Then I have the diffusion constant, which is a squared over 6 pi squared L squared over 6 Lx squared. Okay, so by this inverse transformation, I'm back into the polymer world, and I found the propagator in one dimension, and it depends, as you see, on the mode I'm considering, on the number of monomers, on the size of one monomer, and on the size of the box. I have the expression. If I factorize the same expression, but for y and z, I end up with the 3D problem. The 3 directions are independent. So I found the probability, but wait, in one specific state, one specific mode. If you want to caricaturize a bit that, well, I was asking the question, what is the probability to go from there to there in one step? That was my polymeric question. Now what I answered is the probability to go from one to the other with this mode, which is a sine-like mode if you want. But of course, there is another mode. There is this one. And there is another one which has only one node, for instance, and then plenty of modes, okay? So in a sense, the total probability I'm interested in will be a summation over all those probabilities for specific states, specific paths. Is it clear? So this was the new mode. This is another mode, a new prime. And there are plenty of those, okay? So now we would like to calculate the total P, which is my initial problem, finding the probability to go from R prime into 2R in n steps. So how should I proceed according to you?
We have to know the coefficients in the orthonormal basis.
Right, but then we might do some assumption. You are trying to weight those different modes. So you're saying those modes, they will contribute perhaps differently. But if you think about the polymer problem, not the quantum problem. So I have no wave packet, if you have that in mind, the packet on, right? Now I have a polymer problem. I'm saying I want to know the probability to go from that point to that point in a certain number of steps. I can do that with this mode. I can do that with that mode. I can do that with another mode. What do you think about the respective probabilities or weight fraction of all those proposals? We are dealing with an ideal problem. There is no interactions between the monomers. So what about the conformations, the microscopic conformations in terms of probabilities between them?
They all have the same probability?
Yes, and this is very specific to the ideal situation. Of course, you have something which is very curvy like that, and monomers are close to each other, they will feel the repulsion, the Flory-like excluded volume. If you have now a very convex shape, then you might avoid a bit more the interactions. So if there are interactions, what I'm saying, it will be modified. But without any interactions, I can reasonably say that I can do a partition with equal weight for all the paths. So if you agree now, I can say that, well, the total probability is simply the partition with weight 1 of all the P nu. They all contribute equally in this drawing here, right? Those are all the, if you want, the microstate of a macro state being starting at one point and ending at another point in n steps. Okay, so I think I solved the problem. Now, of course, it's an infinite sum, but I have the solution. What I was looking for was really that guy in confinement, and now I'm in confinement thanks to the analogy with the quantum problem. It will be simply the sum of 3 functions, one for x. As usual, there is separability between the 3 directions. One for y, let me just write them this way, and one for z. And I can provide you one of those, px of x prime, x, and n. Well, in this summation over nu, it's in fact the summation over the triplet L, P, Q of P nu, right? LPQ. So you have three sums, so one for each. So it's the sum over L being positive strictly of, what do we have? We have what we wrote here, this guy. So 2 over Lx, I can put it outside, sine pi Lx over the size of the box. Another sign for, this was for the departure point, for the arrival point now, Lx, and the exponential that is weighting all this, a squared pi squared L squared in mod L, 6 Lx squared. Okay, so thanks to this decomposition, I found, and thanks to the assumption that all the modes are equiprobable, I found the solution of the problem. The solution is the product of the solutions for each direction of space, and for one direction of space, you simply have an infinite sum over all modes, and we know how to write each mode because we solve the quantum problem. There is an exponentially decaying function, and there are two sign oscillatory contributions. Is it clear? Is there any question on that? No? Everyone is with me? Good. So we are now also checking the initial condition. So we would like to check if we really satisfy what we had in mind previously, is that there is a Dirac, and so it means one Dirac for each direction. So again, there is a factorization in the initial condition. So we would like to check that. So it means we would like to check it for any individual direction, and I will check it only for one of those because you see the formulas are all identical. Do we have that as expected normally, right? So let us but just use this expression and replace capital N by 0 and look at what comes out. We have the prefactor 2 over Lx. We have the summation over all positive L's. Signs are not affected, both of them. And then here n equals 0, so it's 1. So we end up with solving that infinite summation. And we have an identity for that. If you look at the formulas in your in the énoncé, the first one is an infinite summation. And I could also put equals to 0. It doesn't change since the L equals 0 here will kill the sign anyway. So I can just extend the bounds and rewrite it thanks to the formula in the tutorial. This is then pi over 2 times the Dirac between the two elements. So pi x prime over Lx minus pi x over Lx, which can be rewritten this way. It's pi over Lx if I kill the 2's, and delta of pi over Lx times x prime minus x. And this, I can put that outside. So to put that outside, it's simply multiply by Lx over pi in front. And you see that they immediately again cancel out with what was already there. So it's really okay. I end up with the Dirac. So I checked that the initial condition is okay for the x-axis, and since those expressions are the same for all directions, you have the same for y and z. Okay, So we are self-consistent. We found a solution that contains the proper initial condition. And so we can start to work with it a bit more and extract some information. So the program is first to study a bit the properties of that expression, see if we recover the Markovian identity in particular, and look at the concentration profile, because this, if it's a probability of shapes, well, we know the concentrations of monomers everywhere in space, thanks to those probabilities. And then when we have done so and introduced the main general characteristic, we will go to a particular case where we start to take the box and confine a lot the polymer chain inside by making the length scale of one direction going to 0. And we will try to see how the entropy, the free energy, the pressure, and so on are modified in confinement. And we will try to extract some relevant information for biophysics and nanophysics. Okay, this is the program for the rest of the tutorial. Do you have any question at this stage? Even calculatory or whatever.
Yes,
yes.
I have a question.
Yes.
It's about the definition of the propagator, because I thought when I looked on the internet,
Yes.
I saw that it was more the green function of the, I mean,
Yes.
the Schrödinger equation. So I would like to know the link, because like you make the propagator kind of appear like this. But,
no, it's a Green's function. It's the same. Yeah.
It's the same?
Yeah, it's the word propagator comes from field theory.
Okay. So because then it would be the solution. I mean, there would be a source term in the Schrödinger equation with the delta function, no?
So what you have here, okay, so it's a very specific question, I understand. So let me just even go here, okay? So here we have a diffusion equation. Mm-hmm. To solve that diffusion equation, we used a condition, an initial condition that was the following one. It's a Dirac. So what we did, if you remember correctly, we solved a partial differential equation with an initial condition. We didn't put any Dirac in the equation like you would do for a standard Green's function, right?
Yes.
Nevertheless, the solution we obtained was the Gaussian, and you might remember that the Gaussian is the Green's function of the diffusion problem. Okay, so this is very specific. This is related to the fact, and it only works for this type of diffusive-like operator. If you try to solve delta F is equal to, let's say, dTF, this is the diffusion equation. If you can also solve it this way, so minus delta F plus dTF, and look for a Dirac in space and time. F would be the green solution here. So this with f of x equals 0, I'm putting everything in 1D for clarity, being a Dirac. So solving the diffusion equation with an initial condition is equivalent for that type of operator to solving the Green's function equation without any initial condition, just everywhere in space and time. You can do that exercise. It's a math exercise for the Green's functions. Okay?
Yes. Okay.
If there is any problem, you just send me a mail and we can chat about the math. Okay? But I tell you that for those operators, it's equivalent to dealing with a point source, or an initial condition, or a forcing in the equation. Okay? It's the same.
Okay.
So you can check that. But if you buy that fact, then let me come back to this. Now, you see, if it's true in terms of symmetries or properties of the operator here, it's true for that as well. So G, that I call the propagator or the solution P, if you want, is in fact the Green's function. It's only specific to Laplacians and diffusive-like operators. This would be broken for nonlinear differential operators and other higher orders of derivatives. Okay?
Okay, thank you.
Okay. Other questions? None? Okay, so let me just comment on two aspects. So question 6 is about the Markovian identity. You remember the Markovian identity? We said in the bulk, it was true in the bulk. If I start at R prime and end up at R in n steps, well, this could be decomposed sorry, I just go down here a bit, should be decomposed into starting at R prime and stopping somewhere in a certain number of steps, and then finishing the process. It's an independent part from S, sorry, and ending up at a good ending point with the remaining number of steps. And of course, I should integrate over all the intermediate points that are possible. So we discussed that extensively in tutorial number 1. You agree with that? This is what we used in order to derive the diffusion equation in particular by doing a Taylor expansion around this Markovian identity. But here now we are in a confined situation, and by analogy with quantum mechanics, we were finding the total solution here. So like we checked the initial condition, we would also like to check that we really have this, because I mean, we are not necessarily sure of that. Of course, we are, because it's a diffusive-like operator. So since the diffusive operator comes from that identity, there is no problem. But just to play with the expressions, we will make sure we understand that. And thanks to the separability between all the directions of space, we will only check the following part, the 1D problem, let's say in X, for instance, and check that we really have the identity. And this was true, sorry, whatever n is. S is now a real number, not a vector anymore. So let me pick one integer n that is belonging to 0 or 0n interval. And then finishing the process in the remaining number of steps in 1D. So between 0 and Lx. This was a 3D integral. Okay, so question, do we have that? And thus, for me, it means showing that in 1D is sufficient. So let us show that in 1D. So we will start from the right-hand side term, this one, and just compute this product. So Px prime S and N, and sorry, here, I forgot to say that it's a 1D part, whereas here it was really the total P. Okay, so Px is, remember, it's 2 over Lx times summation over all possible modes. And then I add sine pi x prime L over Lx, sine pi S L over Lx. Then same here, I have another 2 over Lx squared, a summation over L prime, and then I go slowly. I forgot the exponential part. Okay, I will just keep the exponential here, minus n a squared pi squared L squared over 6 Lx squared. And then I have this guy between S and X, and with another number, L prime, which is also positive, sine pi S L prime over Lx, sine pi X L prime over Lx. And then I should have the same exponential factor, but here with n minus n in front. And careful also, it's not L, but L prime. All right, I hope I didn't put any typos here. Okay. So any intuition on that? What should we introduce to solve that part? You can use the formulas in the tutorial, for instance, at the end. Which one seems interesting? And I'm summing, I told you, over S. Huh? So does anyone see the trick? No? All right, so we will use the first identity provided in the formula, the formulas at the end. As you, the second one, the second identity, when you have the integral of sine mu times sine nu, it's a Kronecker symbol. And we would like really to use the Kronecker symbol because we want to remove one integral here. So let us have a look. If I take that part, then I have pi, I take that part, and I do the integral over S. This will be really close to what I would like to find here because you have a L, and here you have a L prime. So you end up with something which will be proportional to the Kronecker LL prime. And if I have this Kronecker, I can just remove all the LL prime everywhere. And by the way, I would have removed this integral over S thanks to the formulas. So let me rewrite this way. I will just factorize 4 over Lx squared. The summation over L prime, I don't put the bounds anymore, it's obvious. I keep the terms that don't depend on S in front. So there is this one, there is this one. And then you have the two exponentials. So minus a squared pi squared over 6 Lx squared, which is in factor of n L squared plus n minus n L prime squared. Just grouping them this way, it's shorter. And then you end up with what I was suggesting, the integral along S between 0 and Lx of two sines, pi S L over Lx, and sine pi S L prime over Lx. And I should not have forgotten everything there. Yeah. Okay, and this is close to the formula provided. Let me just do one change of variable. So we see that the good variable is in fact S pi over Lx, so I can multiply by pi over Lx and thus by Lx over pi in front here. And since I'm integrating between 0 and Lx for S, it means that if I change variable, it would be between 0 and pi. This is du. This is sine Lu sine L prime u. All right. And so thanks to the formulas provided, this is a Kronecker times pi over 2. All this is pi over 2 times the Kronecker between L and L prime. All right. So at the end, so the pi over 2, you have pi that disappears here, pi and pi. You have 1 Lx that is removed, and you have 2 and 4. So you have 2 over Lx at the end in terms of prefactor. It's equal to 2 over Lx. You have a Kronecker, so you can kill the integral over L prime and replace all the L prime by L. So it seems that you have the summation over L sine pi x prime L over Lx. Same for the arrival point. So it's the same L now, it's important. And so here also the L that was here and the L prime that was here are both equal to L. So I can factorize L out and you have small n plus capital N minus small n. So you end up with only capital N. So you have one exponential, which is this one, 6 Lx squared. All right, and what is this? Well, this is Px starting at x prime, x in n steps. So this is really what we wanted to show. We wanted to show that this integral with a midpoint S integrated over all space was equal to Px, x prime, x, and n. So to go from one point to another point in a certain number of steps, Well, it's going from one point to an intermediate point and then finishing the process. And I integrate over that intermediate point because they are all possible. It's really the Markovian identity. In a sense, the future doesn't depend on the past. So I'm factorizing out the random process. So I go somewhere, and then what happens after doesn't, I don't remember the past, and I just start again a random walk from this intermediate position. All right, so we have checked the Markovian identity. Of course, if you remember that the differential diffusive operator comes from the Markovian identity from the first tutorial, it is expected that the solution satisfies this, but you might have forgotten that fact. And it allows us to work a bit with the basis of solution of the quantum problem. So we are now just checking things. Is it clear? Okay, I take that as a yes. And now we would like to just a comment. It means that I'm interested in the probability to go from one point to the other through a certain path. If this path is touching the wall, for instance here, and ending up here, then this will not contribute. Because of the Markovian identity, going from there to there is going from there to an intermediate point and then finishing the process. And this intermediate point belongs to the wall, and remember the boundary conditions. Whatever the number of steps, if there is an intermediate point that touches the wall, the probability is 0. So it means that what we've constructed here, the total probability Px, which is here, satisfies the fact that there is no possibility for any intermediate monomer to touch the wall. So it's really the confinement problem. I'm really diffusing freely, but I destroyed or I removed any contributions that goes outside the box and comes back, or that simply touches the walls, okay? So it's self-consistent. It contains all the information about my box problem, confined problem. Okay, this is it. And a final formal discussion I want to make before going to physics. It's from the probabilities, we can define the concentration of monomers. So we can take a box. We know there is one chain inside. This we already know, but we don't know where it is. And if we put a probe, we would like here at that position R0 to know what is the concentration of monomer I will find on average. So how could I answer this question? How could I build formally the expression for the concentration? Does anyone has an idea here? So a certain configuration here like that have intermediate points. And this intermediate point can be at R0 or not. But if it is at R0, if there is an intermediate point at R0, it will contribute to the concentration. So how can I relate the knowledge of really the total probability of all the conformations in space and finding a monomer at a very specific position? I can take the probabilities and sum them as much as I want. Do you have an intuition on that? Don't hesitate to propose anything here. Huh? No one? Yes?
Maybe we can sum on the initial position, sum over the number of monomers smaller than the total number of monomers, and correct, say that at the end it arrives at R0. Close,
not necessarily at the end. So in fact,
yeah, but it's similar. It's
yes. So I think you have the correct answer. So it's exactly that. Finding a monomer here, because this is what we are dealing with. We want to know the concentration at a certain point R0, which means finding a monomer at this position. Well, if we find a monomer here, it means that somehow there was a random walk like that. somehow. Could be another. It could be another one, of course. It could be a one that starts somewhere else and that ends up strictly here, or that starts here and goes somewhere else, whatever. But for sure, we should have a chain that passes through that point. That's a necessary condition. So as your colleague said, then it must be that C of R0, that is the quantity I define here, must be somehow proportional, and we will look at all the details after. The probability of starting somewhere going to R0, I must pass by that point to find a non-zero concentration in a certain number of steps, and then finish the process from R0 to the final point in the remaining number of steps. And as you said, well, this starting point doesn't matter, this ending point doesn't matter, so I should integrate over all possible starting and initial position. Really what I want to know is if there is a monomer here or not. I don't care where the chain has started and where it ends up. So what I want to do is to integrate over both the starting and final points, correct? And you also mentioned something important. I also want to make sure that the monomer could be at the beginning, it could be at the end, it could be right in the middle. So I also have to sum over n. So n should be summed between 1 and capital N. It could be either the first monomer or the final one, okay? Is it, so it's a very good suggestion. Is it enough? Am I sure that it is the concentration? I mean, is there a prefactor missing or? Are we correctly normalized? Stated differently. So by what should I normalize?
The volume.
That is correct. But so this is the quick and exact answer. But let's put it in an intermediate step first. So I should integrate over all possible random walks in this box, even those who are not touching the point I'm considering. Okay, all those ones, they should be also integrated. To have a proper concentration, if you want, I want to have a certain fraction at the end. I want to make sure that it's correctly normalized. So I should sum over what? Over all possible random walks, starting at R prime, ending up at R, whatever their intermediate points. So that I'm pretty sure that it's normalized. Is it okay for everyone? And each of those integrals are triple integrals because we are in 3D. And as you said, if we are in a very large box, in the bulk, this becomes the partition. This is the partition function, sorry, but in the bulk, the partition function is the volume. This we already discussed that. So you're right that in the bulk, this will be the volume. So it's a good intuition. But you will see that it's not the volume anymore when I'm very confined. And this is the objective of the last part of this tutorial. Is there any question on that formal expression? Do you understand all the ingredients in it? Or don't you understand them? Okay, so let us continue then. We can do a final check. What do I want to ensure? Mass conservation tells me that if I now integrate, it's a triple integral over all possible points. What should I get? I have a concentration profile in my box, but I integrate over all possible points in the box. What should I get at the end? It's a monomeric concentration profile.
We should obtain N.
Yes, this is the normalization we should expect. So this is mass conservation, okay? So let us check that. Can we just use the formula above and integrate it over R0 and invoke some relation to check that? Okay, so you have the sum, so the integral of C over R naught is equal to the sum over n equal to 1 towards n. Then you have this integral over R naught of this double integral over R and R prime, going from R prime to R naught in n step, finishing the process from R naught to R in n minus n steps, and normalizing properly, no matter the intermediate point. Okay, so I just added, if you want, this because I added it here. So I integrated over R naught. So what property should we use now? Straightforward. I don't hear you, Baptiste. You said something, Baptiste?
No, we were just.
Okay, so there's not a problem of mute or not. Okay, so what formula should I use according to you?
I mean, we should integrate over R naught and use Markovian equality, and like this it gets 1 to sum and n.
Yes, perfect. So we just do that. We inverse the two integrals, or I should say the 9 integrals. So those 3 should go here, and I recognize the Markovian identity here because I integrate over the intermediate point. So this is equal to n equal 1 to n of dr prime dr of, well, due to the Markovian identity, this becomes simply starting at r prime, ending at r in n steps. And I normalize by, well, the same thing. So this is 1. So I end up with n. Okay, so this is really a check that we put the good normalization here. Okay, that is why we recover the mass conservation properly. So there was indeed a denominator that we should not forget. Okay, so now the status is the following. We've identified our problem, a single polymer chain in a box with proper boundary conditions, and the chain cannot be outside the box. Okay, we transform that into a polymeric problem because the operators describing the two, into a quantum problem, because the operators describing polymer and quantum world for a particle in a box are the same. We solved the problem in the quantum world. We went back to the polymer problem and obtained the general solution for the probability. And we checked various things. The initial condition is correct. The Markovian identity is satisfied. And we constructed an expression to have the concentration of monomers. Okay? And it seems to be correctly normalized. Mass is conserved. So we have now all the tools to look at physics. Really, what happens if I take a box that is so small that it becomes comparable to the size of the polymer chain or even smaller? Then the conformation will be restricted. What is the pressure, for instance? Does this chain exert some force on the walls that I can measure with a probe? What is the value of that force in Newton? Okay, that's an important question for biology and nanophysics. So this is the goal of the last part. So I'm talking about confinement. So according to you, what is the criterion to say confined or not confined? Remember, it's an ideal chain. So what is the typical extent of the ideal chain?
Okay, so the Lx and Ly and Lz should be very big compared to square root of n.
Correct. So just to estimate things first, in the bulk, we have a certain size for an ideal polymer walk. It's square root of the number of monomers times the size of one monomer. Okay. If the box is much bigger than that, well, we will live in a bulk situation that we already discussed in the tutorial number 1. So the confinement situation is in contrast when this starts to be comparable or even smaller. Okay, so the criterion for being unconfined is this one. Okay. Okay, so what is the partition function then? The partition function, we introduced it at the beginning, is simply the integral over the starting and ending points of the probability we already calculated that at the beginning. This is equal to the volume. So as one of you said, the denominator here should be typically the volume. Well, this is true in the non-confined situation again, okay? This is only true in the non-confined situation. It's not true in general. But here we see that it works. So the partition function is really the volume. And this is one first thing we can do. We have the partition function. What is the entropy? Remember, we are in a canonical ensemble. So what is the entropy if I know the partition function? Or in canonical ensemble, it's KB log the partition function. Okay, so what do we have here? Well, we have KB log the log of V. The log is the Neperian logarithm as usual. Okay, so the free energy, there is no interaction energy in that problem. There is no enthalpy in that problem. So it's purely entropic. So the free energy is minus TS only. There is no internal energy. All the configurations are equiprobable, as we discussed. All right, and thus the pressure is equal to minus the derivative of the free energy with respect to volume at a constant temperature. So the pressure here is, and then there is 1 over V. Pretty easy. The bulk situation is pretty easy. Any comment on the result? What is this law?
It's an ideal gas.
Yes. Why do we recover an ideal gas in a sense?
We have no integration and no interaction, sorry, and we are not confined, so we can consider as our points.
Yes, and moreover, this is specifically due to the analogy with the quantum problem. We can, I mean, we have plenty of monomers inside the chain. There is no ideal gas here. It's a polymer problem. It seems it has nothing to do with the gas. But there is a direct mapping between the polymer problem and the problem of one particle of a gas inside a box in a quantum world. And so we recover the law for the gases that you could obtain from Schrödinger's equation. Okay. In stat field. So we really end up with the fact that the pressure is really the pressure as for an individual particle of an ideal gas. Okay. More practically, it seems then that if you have a polymer chain, you can remember that the typical pressure it would exert in the force per unit volume, the energy per, the force per unit surface, sorry, will be comparable to kBT divided by the volume. So when the volume tends to infinity, there is no force exerted. But as you start to reduce the sample size, well, the chain will, for entropic reasons, it doesn't like to be confined. It will try to expand, and it will push, really push on the walls, and you might be able to measure that with proper apparatus. Okay. What is the concentration profile then? So the concentration profile, first, before doing the concentration profile, let me just comment on one fact. The pressure, the pressure, I'm tired. The probability starting at x prime, ending at x in n steps, which is my elementary observable. Remember its expression, it was sum over all modes. There was a factor in front, and then a product of sign. It's always the same long expression, but there is nothing complicated in it. And this exponential minus n a squared pi squared L squared over 6 Lx squared. Okay, this is this guy. So can you comment on its approximate expression in a non-confined situation? What can I do if I'm in a non-confined situation?
It becomes x squared, x prime x, and the two signs, because Lx becomes infinity, so we can.
Careful, I have also that. Huh?
Oh yeah.
Should be careful. It's an infinite sum. So now you have a conflict between two infinites. Not clear. However, well, I mean, you're right. In fact, we could develop that and approximate that. In fact, I think you're right. For very specific.
It's because the exponential decreases very quickly.
Yes, but the thing is that I have the right to consider, you know, x can be anywhere. So I can also look at x going to infinity. No?
Yes.
So in that sense, x over Lx is finite, in fact. I can have a box, and I can say I'm always at the midpoint between the center of the box and the wall. Now, if I take that the wall goes to infinity, well, the midpoint goes to infinity. So it's not clear I can tailor expand the signs, in fact. So I would say no, in fact. What else? But this idea is good. Can you do it on the other factor? Well, here, what do you think about that guy? It's an exponential, so it goes rapidly to what?
0.
1. Yes, thanks. I see some videos. So yes, this is the same kind of stuff. This will be most probably 1, and there is no x or x prime in that. So okay, so I can use your trick, but in this one. Okay, so what about the expression C of R0? Remember, let me just put the formal expression first. Is the sum over what? Over n between 1 and capital N. What did we say? We say we have to integrate over starting and final point. And then we had two stuff, P R prime R0 N, P R0 final point, remaining number of steps. And we were normalizing, right? And we were normalizing by Z. Let me just put back Z because now we've calculated Z. Okay, so now I can rewrite this into Z, I know it. And I can factorize this into 3 dimensions of space. They are all equivalent. So you have, by the Fubini theorem, you can have x integral, y integral, and z integral separated. So you have 3 factors, and Ix is what? Ix is the integral over, well, it's the 1 diversion of what's above. Sorry, there was a typo here, no prime. P of x prime x naught n, P of x naught x n minus n. Okay, and now I can replace this by all the expression above. So I have 2 over Lx, which is squared. I have a sum over L and a sum over L prime of sine pi x prime L over Lx, sine pi x naught L over Lx, then sine pi x naught L prime over Lx. Sorry, it's a bit long. Sine pi final point L over Lx, L prime, sorry. And I have no exponential because it cancels to 1, okay? And did I forget anything else? I don't think so. Yes, no, it's okay. All right, so what can you do here? Well, you can do the, let me rewrite the L prime and L integral separately, or summation. So, I will remove that. So I can do those independently thanks to the formulas I have in mind. This is L, and I will do that first, and I will also do that besides, okay? So let me take another whiteboard. It's the double integral of 4Lx squared and then what is this? So if you look at the formulas, it's the first one provided. So in a sense, it's pi over 2. So yeah, there is a pi over 2. And then you have a Dirac of pi x prime over Lx minus pi x naught over Lx. And so this Dirac is pi over 2. And the Dirac is in x prime minus x naught. So I can multiply by Lx over pi and remove the prefactor. So it's Lx over pi. Okay. Then I have the second one, which is also of the same form. It's pi over 2, so I can just add a pi over 2 here. Then same thing, Lx over pi will pop out. And then I have a delta of x naught minus x. Okay, and I can cancel a few things out. Pi is not here. Lx squared and Lx are removed. I have factor 4 that goes away. Everything goes away. And I have two integrals of Dirac, so this is 1. Ix is equal to 1, and so it's also true for Iy and Iz, by the way. There is no privileged direction. So in this stuff, you end up with the fact that the concentration is the sum over n of 1 over z. The concentration at R0 is the sum over n of 1 over z, and 1 over z is 1 over volume, as you correctly pointed out, and so it's n over v. Okay, all that for that. We end up with the fact that the concentration is uniform in the bulk, and it's equal to the number of monomers divided by the volume that is exploding, so it's a concentration that is finite because you also have a polymer chain that is a priori very large, infinitely large at the thermodynamic limit. Okay, so basically it's expected. There is no privileged position in this problem. It's spatially invariant. There is no wall, no boundary, etc. The interesting part comes now. I will now start to confine the wall. I mean, confine the problem in one direction. Let's say I will use the x direction as the confinement situation. So we will now be in a situation where you have really a sheet, like y and z will be infinite. It's really a bulk problem in the y and z direction, but in the x direction, I'm really confining the sample, okay? So in confinement, I will assume that Lx becomes smaller or comparable to whatever square root NA. And I keep the fact that Ly and Lz are much bigger than the size of the polymer chain. And in fact, I will even go to the maximum limit. Huh? This is purely mathematical. I will also assume that I'm confining so strongly that I'm really smaller than the unperturbed size of the polymer chain. Okay? But we can look at the transition. It's interesting. So we are now in that specific situation where X is the confinement situation. So Pierre-Gilles Degene was saying, okay, so now we are in a ground state dominated problem. That's a big jargonic expression. Why, according to you, he's saying that? It's a polymer problem. So why does he talk about ground state? Or
because when we look at the expression of px prime xn, it's the dominating terms in the exponential are the one with a smaller l. So
that is correct. That is correct.
State,
That is correct. So instead of having this expression going to 1 because NA squared is very small compared to the box, we are in the reverse situation where now this is very large. If you want, this number NA squared over LX squared becomes very large. So it's, let's say, infinite. Minus infinite in an exponential provides something really vanishing, okay? So now you have L. So the larger the L, the faster the exponential will vanish to 0. So it seems we are dominated by L equal 1. This is the largest term, and the other one are exponentially smaller. So this is a very good point. And this is why in the quantum vision of the problem, it seems that we are in the ground state. The problem is dominated by a populated ground state, and the excited states don't matter. Okay, so it's, if you want, for the string, the guitar string, it's the simplest, the zeros mode. Okay. All right. So this is the exact, the correct answer. So Px, we will assume it, and it's the same for y and z again for all directions. We will assume it to be mostly provided by L equal 1, which means that you only have one term in the sum, which is a great simplification. And sorry, there is no L, it's 1. So it's even better. Up pi x over Lx. And I should keep this little phase, but it's a constant. L squared, pi squared, there is no L anymore, 6 Lx squared. So purely parametric here. So it's interesting, now I have really a simple expression. When you are super confined, you are dominated, if you want, in your summation over all possible modes. In fact, you are not equiprobable anymore, or there is no equipartition between all modes. You are dominated by one mode. So everything is as if you were working in the ground state of the quantum problem. So the ground state is this one. Here you have the complex conjugate, and you have the energy of the ground state, which appears here. That is why it's called a ground state problem, despite the fact that it's a polymeric situation. Okay, this is great because we can do now a lot of calculations with that simplification. In particular, we can revisit everything we did so far on the thermodynamic sense. Okay, so let me take another whiteboard here. The entropy. So remember, the entropy is defined from the partition function. So let us start with the partition function. The partition function is dr prime dr PR prime. This is always the definition, is the sum over all the probabilities. This is the normalization, the partition function, so this is clear. But now we would like to show that it is not the volume anymore. That's the difference with the bulk. So again, this is really a separable problem, so I can transform that into Zy and Zz with Zx being, as usual, the X problem. Okay, for which we now have a simplification. And this, well, what about those guys? For their case, for their directions, there is no confinement. It's really a plane. So for Y and Z, we are really in the previous situation. So it's the volume if you want, okay? So this is Ly, and LZ, we already performed that calculation. And there is no change for those guys. So if you want, I can transform that into Zx over Lx times Lx, Ly, Lz, which means volume. So the partition function is the previous one with a correction factor, which might not necessarily be equal to 1. So it's not the volume anymore. So this is what I want to calculate. I would like to calculate Zx over Lx. So let us go on. This is the integral over x prime and x of Px. And Px, remember, I have the ground state approximation, which is written here. So I will only keep the ground state now. So it's 2 over Lx. And you have sine Px prime Lx, sine Px pi x, and a constant. That goes out of this double integral. So I'm left with the prefactor and then a product of two identical integrals, dx sine px over lx for x going from 0 to lx, everything squared. It's the same. Okay, and what is the value of that? Well, we can do some change of variable here. So pi x over lx, so I can put a pi here, lx, and multiply by lx over pi. Since there is a squared, there is a lx squared over pi squared that jumps out due to that guy. And then, so this is a new variable that I can call u, and just it goes from 0 to pi. Okay, so I'm left with the integral of a sine. Sorry, what did you show? No, I missed. I saw something on the video by Baptiste, but no.
No, I was just commenting with Leo.
Okay, perfect. All right, so we have here, what is the value? The value of the integral of a sine. Well, it's the primitive is a cosine. Between 0 and pi, it will give 2. And there is a square, so this is 4. Okay, so you end up with the following expression: 2 times 4 is 8. L squared vanish, and you have pi squared and an exponential. So this is Zx. And no, I made a mistake somewhere. Here, there is careful. There is a typo here. There is, I don't know why a squared appeared. It's wrong. There is no square here. So it seems that there is something missing, which is something linear in. It should be proportional to a length, right? Look at it was a volume before, so Zx should be a length. So there is a Lx missing here in front of the exponential. Okay. Which means that Zx over Lx, which is the thing I'm interested in, is this guy. So I have the correlation factor now. All right, so if I have Z, I have S. S is equal to KB log of Z, which is KB log of the volume, which is the unperturbed part. And now there is a correction, so plus KB log of what? Of 8 over pi squared plus KB log of minus n squared pi squared. So I will remove that. Sorry? Sorry? I heard something? No? Okay, there's a problem with the microphone, thanks. I will remove the log and put a -1 in front. Here we go, and what is inside is n squared 6 Lx squared, if I didn't forget anything. All right, so I can just say S is equal to S bulk, which is this guy, plus or minus, I should do something, a constant. And I put it this way so that the sign is obvious. Pi squared over 8. And something positive with a minus sign in front. So in a sense, I'm pretty sure that this is inferior to S bulk. Is it expected?
Yes.
I'm restricting the number of conformations. I'm confining the chain so there are less accessible conformations. Okay? So the entropy gets smaller. I have a less amount of microstate. So this is the entropy. Can I go to the afterward the free energy now? F is minus KB T log of Z. So something here appears. So there is an additional energy. Of course, I'm restricting the number of conformations, so the system gets frustrated, and so the free energy increases. Okay. So this is F bulk, the one we already discussed before. I changed the notation just to make it different from the confined case. There is an extra constant. Okay. It's a constant that is positive. And then there is an important part, which is a function. So let me put the scaling first. It's na squared over lx squared. And then you have some prefactor that is meaningless. But the main part is this. So the reference, F, is here. Adding a constant to a free energy doesn't change the physical properties because the variation won't be affected by any constant reference. So what we are saying is that when we confine a chain, there is an additional contribution that I can call delta F. And delta F is, I need a new whiteboard here. Delta F is what I just introduced. And I neglect the constant that appeared in the problem, is basically only KBT times square root of n times A over Lx squared. Can you comment? Does it ring a bell? Does it remind you of something? Remember the entropic elasticity in the first tutorial. In the tutorial 1, we were taking a chain that was in the bulk, and we were pulling on it to extend it by, let's say, a certain size R. So we were saying F is typically KBT times R divided by square root of NA squared. This is a reminiscence of the Gaussian probability, if you want. It's what is inside the exponential, right? So we were saying that if you want to take a polymer chain and now stress it, extend it, thanks to the fact that you are reducing the number of microscopic conformations, you increase the energy by an amount delta F, which is proportional to KBT because it's an entropic effect. It's purely related to the number of conformations. And then we saw it was a spring. It was R squared, and the stiffness was provided basically by the undeformed size of the polymer chain. Okay, look at the expression above. In a sense, it's kind of the opposite. I have the size here, and then now the confined length is here. So now it's the I have a chain, and I try to put it in a very small sized box, okay? But I pay again the same kind of penalty. But now the term they appeared reversed, okay? So now you know, if you work with such systems, thanks to the confinement effect, you know that you are ground state dominated, and so you have the typical free energy. The free energy, you will pay a price by confining too much a chain, and this price basically is the squared of the typical size divided by the confinement length. So you should remember that scaling. This is the physics behind. Okay, we can even calculate a force associated to that. So the force along X is minus the derivative of delta F with respect to Lx. It's really like the pressure, but now we have anisotropy, so we don't talk about pressure anymore. We have a force in one direction and two forces in the other direction. And so what do we get? If we take the full expression, there should be here sorry, it's far away. You have a pi squared over 6 in addition. So there is pi squared over 6. And then I derivate delta F with respect to L. So I have kBt n a squared. And then I have Lx. So it's Lx squared. So Lx cubed with a factor 2 here. And so it's pi squared over 3 kBt n a squared. So we have a force. Now you take a polymer chain, you put it in a box, there will be a force that pushes on the wall that you can measure if you have a very fine probe. And this is the scaling with Lx. Let us estimate things. So this pi third, so it's a pi squared, sorry. So this is typically 3. kBt at room temperature is 4 10 minus 21. N is, let's use the same orders of magnitude as previously. So 10,000 monomers, each having a size of 1 angstrom or 2 angstroms in the tutorial. So 2 to the power. So there is a 4 that appears, a 10 minus 20. And Lx, we confine the box by a few nanometers. And in the tutorial, they say 5 nanometers. So 5 to the 3, and then 10 minus 27. 5 to the 3 is something like 100. So this is 4. 3 times 4 is 10. 10 over, so it's 1 over 10. So 10 minus 26, and then 10 minus 41. So this is 40 pico. All right. So we end up with a 40 piconewton force, which is comparable to the type of forces we estimated for DNA or polymer chains in general. It's the piconewton range. The force needed to extend it by its typical size is that range. Okay, so this is a force that is really accessible by plenty of methods. Optical traps, for instance, you can measure forces down to the femtonewton scale in water. AFM, you can go to the piconewton range. So there are plenty of methods, right? So it seems you could really confine one polymer chain like DNA and start to compress it so that you have less and less configurations, and you measure this anthropic force that is exerted on your probe, and you will find these orders of magnitude. All right, final point, and I think I will stop here because I can let you do that as a homework. So homework, calculate the concentration profile. We want to calculate that from the ground state dominated expression. So you have everything. We would like to show that it is typically provided by a sine squared. So it should be related to the, if you want, let's call it phi x. So what was the notation again? It's phi 1 along x. And then should be proportional to something like that. So in a sense, it should be proportional to the norm of in the quantum problem squared of the wave function in the ground state. This is the probability of presence. And so you will end up with the fact that the concentration is proportional to that. So this should be sine pi x naught 1 over Lx squared. Right, and you will find all the prefactors because you have all the expressions. Okay, but it is expected that we find the norm of the ground state to the square, and this is what it's 1 minus 2 pi x naught. Sorry, cos 2 pi x naught Lx squared, everything over 2. So if I go near the wall, small x, this will be something like proportional to a quadratic function. And there is no Lx squared. Sorry for my typo. I'm going quick here. There is no Lx squared, so it should be quadratic in a dimensionless ratio. That is something like that, plus a constant here in factor. Okay, so what it means is that if you are now in your box and you're plotting the concentration, and you can normalize it by well, no, let's not do that. You should end up with some cosine shape. So it's more like a Gaussian, but it's a cosine. This is Lx, this is 0. And what, instead of having a bulk, this is the bulk reference. Well, what the presence of the wall generates is an overpopulation at the center of the box and a depletion at the boundaries, at the borders, due to the fact that all the conformations are in fact folded. Since you cannot go outside, you have to fold you back, and so it depletes the region near the wall. Okay, and so it seems that if you are now able to look at the statistic of probability of your monomers inside the box, you will see less monomers near the walls than at the center, and there is no repulsion force. It's purely entropic. Okay, I will stop here. I'll let you do that and come back with questions by email if it's not easy to do. And I thank you for your attention. Do you have any comment or question? Everyone is hungry? Have a good day and have a very good weekend then. See you.
Bye.
Bye.
Thank you. Bye.
Thank you.